So I direct the Sustainability and Nanomechanics Laboratory. And really what we want to be able to do is to understand fracture in complex materials. And there are three major areas. And I'm going to present just on high performance structural materials. And then we have geological materials and biomaterials. So in terms of outline, I really want to kind of highlight what are some of the grand challenges facing a lot of countries, including the US and the African continent. And then try to think about what are some solutions that are provided that uses and that rely on nanotechnology, and highlight also some promising routes moving forward and conclude. So let's look at the challenges in infrastructure. So we can kind of classify them into three areas. One of them is supporting urban growth. Another one is going to be fostering sustainability. And then finally, it's going to be boosting resilience. So when you think about urban growth, we were talking about earlier the United Nations Sustainable Development Goal. So here we have two goals that are relevant. So the first one is going to be Goal 9, Industry, Innovation, and Infrastructure, which is to build resilient infrastructure, promote sustainable industrialization, and foster innovation. And then the second one will be Sustainable Cities and Communities, Goal 11. This is to make cities and human settlements inclusive, safe, resilient, and sustainable. Now, what does that mean when we think about urban growth? If we look in the United States, this is actually summarized by the US National Academy of Engineering Grand Challenge, Restore and Improve Urban Infrastructure. And that challenge is targeting three areas. One of them is there's a strong aging and failing infrastructure to restore. There's also the need to protect against natural disaster and terrorist attack. And finally, we really have to think about megacities. Now, megacities are very important when it comes to the African continent, because Africa is really experiencing this kind of growth where you have a lot of people that are growing and concentrating in urban centers. So we have a rapid growth of cities, and that's actually boosted by the growth in the urban population, AKA over there. So by 2025, more than half the population in Africa will be under the age of 25. And by 2050, 1 in 4 people will be living on the African continent. Right now, it's 1 in 6 people, 1 out of 6. This is going to accelerate. So by 2100, 1 out of 3 people will be living in Africa. And 10 of the 20th largest cities will be in Africa, and Africa will account for more than half of the global growth. So really, when you think about urban growth, the African continent plays a major role in this case. So let's go look about the other area, fostering sustainability. Well, when you think about it, cement is actually not very clean. It's actually contributing a lot to the CO2, to climate change, to the point that the cement industry accounts for 8% of man-made CO2 emissions. And there's an acceleration because 10 years ago, it used to be 5%, this figure. And that is because the production of 1 ton of cement is releasing 1 ton of CO2. And that is really due to the way cement is being manufactured. One of them is we need to heat the raw ingredient at really high temperature, and the reaction itself is going to release a lot of methane. In this case. For boosting resilience, some of this is actually accelerated by the drastic changes, the climate change, and also just kind of geopolitical events. So we can think of it in terms of extreme heat and heat waves, flooding, natural disasters, and terrorist attacks. For heat and heat waves, this is actually a global heat map from 2020, showing that we had several locations that experienced temperatures above 100 degrees Fahrenheit. In the US alone, for instance, this is going to lead to accelerated wildfires, serious infrastructural damage, but also heat-related death. And if you think about flooding, in the US, there's an significant increase in flooding, but also in flash flooding. And on the African continent, cities and urban centers are regarded as just like hotspot for an increase in flooding. And usually this flooding is going to be accompanied by significant infrastructural damage. There's a significant portion of the population that just backslide into extreme poverty when there's a flooding, and then you have the spread of diseases. So if you were to summarize, we really need to have novel construction materials that will enable us to reduce the carbon footprint of the construction industry. That will be scalable, cost efficient, resilient to extreme weather in terms of heat, cold, and also in terms of water ingress. So let's try to think about a couple of solutions where nanotechnology is going to come into play. And I'm going to highlight 3 of them and then move on to what I see for the future. So I'm going to talk about nano-reinforced Portland cement, then recycle aggregate concrete. So the first 2 examples, we're still kind of a little bit conservative, trying to think about how can we retrofit cement or recycle it to make it cleaner, greener, more environmentally friendly. And then the third one is just to say, well, the problem is cement, so we have to erase it and really find an alternative. So In terms of nano-reinforced cement, so the idea is really to use carbon-based nanomaterials. It could be multi-wall carbon nanotube, carbon nanofiber, helical carbon nanotube, or graphene nanoplatelets. Really, one of the reasons is this high specific surface area, as it was brought before, but also because we have a high tensile strength. So really what we want to be able to do is to activate and catalyze reaction taking place, for instance, the hydration of Portland cement, but also reinforce from the molecular level and add some multifunctionality. So these are some samples that were cast in my lab. And you can see under the scanning electron microscope, as you can see, you have the hydrated cement, and then you're going to have the nanomaterial, either the graphene nanoplatelets, the multi-wall carbon nanotube, or the carbon nanofibers, just kind of reinforcing it. Now, some of the challenges is just the processing. And in my lab, we've really tried to look at different ways to be able to improve the processing, different ways, because nanomaterial, they really like to stick together, but you want to have them uniformly dispersed. So you really want to always break them. How do we disperse it? And whatever process that you have to think of implementation at the industrial level. Is it scalable? Is it readily available? And what about the cost? So these are some of the parameters that we are thinking about. Now, let's look at some of the results that we've seen. So we've seen that the nanomaterial in general are really going to be really good to increase the resistance to water penetration. So we observed that we have a reduction of 70% in both the porosity, but also in the water absorption. We noticed a significant improvement in the fracture toughness. So the fracture toughness is going to be a measure of the resistance to fracture and to crack propagation. And also we looked at what happened when we have the resilience to elevated temperature. And that was very interesting to see that when we look at cement, nano-reinforced cement, in this case, we use graphene, even after heating at 400 degrees Celsius. So 400 degrees Celsius is like simulating a low level, low intensity wildfire. So even after that, it still outperformed regular cement in this case. So we really have a good performance. And to try to understand it is because we have, in terms of the fracture, we have a wealth of micromechanisms that are being developed to be able to counteract and slow down the progression of fracture. But also you have this reinforcement that is occurring at the molecular level, as we've seen using the scanning electron microscopy. And the other point is because due to their high specific surface area, nanomaterials are going to change the reactivity of Portland cement and accelerate it. And this is going to change the basic DNA. So if you think of Portland cement, we can really break it down to having the genome of it. And the basic genome, you're going to have low density calcium silicate hydrate, high density calcium silicate hydrate, and calcium hydroxide. And what we noticed is that when we use carbon-based nanomaterial, we increase the fraction of high-density calcium silicate hydrate and calcium hydroxide, which translates to better mechanical performance, but also to better durability. So this is what we can do if we still try to work within the confines of Portland cement. Another approach is to try to say, well, let's try to recycled cement in this case. And one of the reasons is to think of construction and demolition waste. So if you think when you have an aging infrastructure, like in the United States or even Europe, when you have to demolish those buildings, what do we do with the waste? Well, that waste accounts for 30% of the solid waste, and most of it goes to landfills. And the idea is, well, if we were to be able to reuse it to produce new concrete, well, in that case, we alleviate the pressure on landfills, but also we lead to a process that is going to be greener and more environment friendly. Well, let's try to see what would happen. So typically, you start with concrete, and then you're going to crush it. After different level of crushing and sieving, then you're going to create a new aggregate. And now we can compare what would be a normal aggregate, natural sand, to a recycled concrete aggregate. So in the aggregate coming from previous concrete, you have the parent aggregate, sand aggregate, you have the residual cement, and you have a lot of cracking and a lot of porosity. So just using old cement to make new aggregate is just going to complicate a lot of things. Now, once you use this aggregate and you're going to mix new cement, so you're going to have recycled aggregate concrete. Again, this is going to be different from the pure natural sand concrete because you're going to have the old aggregate. So you have the old aggregate, you have the cement, and now you have a lot of interfaces. The interface of the old aggregate with the new the old cement, and then the interface of the old cement with the new cement. And all of those interfaces, you're also going to have a lot of porosity and a lot of cracking. So we tried in our lab to use nanotechnology-based characterization method to try to understand and compare the properties between natural sand concrete and recycled aggregate concrete. Now, some of the challenge when you think of recycled aggregate concrete is really the processing. It's always a challenge. And then there's overall poor performance. There's a higher porosity, higher water absorption, lower durability, lower strength, and lower toughness. And what we saw in our lab, and this is where we use, again, machine learning method to try to really understand what is the basic genome, if you want, of normal concrete versus recycled aggregate concrete. And when you compare it, we see that for normal concrete, you're going to have a high fraction of high density calcium silicate hydrate and also a high fraction of ultra high density calcium silicate hydrate along with hard aggregates. But when you look at recycled aggregate concrete, then you have very few hard aggregate and a higher fraction of low density calcium silicate hydrate in this case. So you already have a different makeup at the nanoscale and also molecular level. When you look at the porosity, when you look at recycled concrete aggregate, there's going to be a higher fraction of a higher gel porosity, but also a higher capillary porosity, leading to a higher total porosity and a higher relative fraction of the CSH gel porosity. And finally, we were looking at the creep properties. So the creep is measuring the long-term performance. And what we saw is that when you're going to have, on the one hand, you have natural sand concrete, and the other one, you're going to have recycled aggregate concrete. Natural sand concrete is going to have high value of the creep modulus compared to recycled aggregate concrete, which means that if you were to have two structure, one with regular Portland cement and the other one with recycled concrete, when the structure with recycled concrete is more likely to deteriorate more faster and degrade also faster because of those differences. So in my lab, what we're working on now is just to try to understand how can we use nanomaterial at different level to be able to improve the performance of recycled aggregate concrete. Now, another approach, I really want to look at green cementless concrete because the issue is to say, well, the problem is cement. So we really need something that is better to start with, something that has a lower CO2 footprint from the very beginning. And then this is what we're going to be using. So one approach is to use geopolymer. And the way to make it is to mix a source of aluminosilicate with a potassium silicate solution and add fillers. And this is going to lead to geopolymer composite. So now some of the application of geopolymer, so I said a green alternative to concrete, green alternative to cement, affordable housing, additive manufacturing, passive cooling, but also recycling of industrial byproducts, for instance. In my lab, we really try to understand basic structure property relationship of geopolymers. So one of them was just to understand what is the origin of the strength in geopolymer. So we started by building a conceptual model, a multi-scale conceptual model, going from the macroscopic level to the micro and also to the nano level. And this is where we found that there's really this dual role of porosity, where if you look at the micro and nano scale, you're going to have a microporous matrix, and the matrix itself is going to be nanoporous. And the micropores, in this case, are going to be detrimental, and they are caused by processing. So we can reduce and remove them by optimizing the processing routes. But the nanopores, we want to keep them because what they do is just to promote energy dissipation through rearrangement at the molecular level and nanometer length scale. And those nanopores actually can be tailored by adjusting the chemistry and the mix design that we have. Next, I looked at what can we do by using carbon-based nanomaterial within geopolymer. These are some samples that were cast in my lab. And this is what it looks like once we have a multi-wall carbon nanotube, for instance. One of the challenges is always figuring out how do we disperse them and how do we have them homogeneously distributed within the matrix, the geopolymer matrix. Well, overall, we had an improvement in mechanical response. So we had higher values of the indentation modulus, higher value of the indentation hardness, higher fracture toughness, that is fracture resistance, but also higher creep response that leads to the long-term property and long-term mechanical performance. Now, when you try to understand why do we have it, for the fracture performance, for instance, we can link it to the presence of nanomaterial that will be bridging the crack. So this is what we can see. We have, in this case, multi-wall carbon nanotube coming out from the edge of the crack, and that are really actually bridging it and keeping it together. This in turn is going to lead to a roughening of the crack, but also to other toughening mechanisms such as ligament bridging. Another aspect is because of the high specific surface area of carbon-based nanomaterials. And this is going to lead to a higher reactivity of the geopolymer slurry as it's going to harden. And as a result, we're going to have a denser microstructure where we reduce the porosity, but also we are tailoring the porosity. So we are making it less porous and we're making the pore also coarser. And this actually property can be useful when you're thinking about filtration devices, for instance. And then we were talking about matrix densification because we have this high reactivity. So what we are observing along, for instance, the wall of carbon nanofibers is that we have the formation of geopolymers because of this high specific surface area in this case. Now, some of the next steps that we have for nano-reinforced geopolymer is really to try to see how can we have advanced nanofiber reinforced composite using immersion electrospinning. So the idea is really, instead of using carbon-based nanomaterial, we're really going to have a needle and we're going to go within the geopolymer slurry and directly we're going to print the reinforcement. It can be a polymer nanofiber, for instance, as is seen over here. Yeah. So these are some of the next steps that we are exploring. But now I want to kind of shift gear and talk about looking forward. Looking forward, one thing that would be very important is the local material concept. And this idea of local was really illustrated when we had a lot of supply disruption caused by the pandemic, but also by recent geopolitical event. So the local material concept, the principle is really to use locally available raw material to lead to a greener process. And actually, the idea is coming from my collaborator. So I am from Cameroon, and I'm collaborating with Dr. Eli Kamso in Cameroon. And he's the one who really brought that. He's working at the mission for the promotion of local materials. And the idea was, how can we, instead of importing Portland cement, how can we valorize local raw material and still yield construction material that we have equivalent level of performance or even better? How can we, in this case, we are looking at an equatorial weather that has high humidity and where actually Portland cement is not very well suited. So how can we use local raw material? So going back to how do we make geopolymer? So this time we're going to use calcine clays that are sourced locally. Then we have sodium silicate solution. We are going to use feldspathic rocks again that are coming from local sediments. And we want to be able to have a sustainable binder. And we have a collaboration together. So what we've been doing a lot is just my colleague has been working on synthesis and processing, and then I've been working on characterization. Some of the questions that we've been asking, so one of them is really porosity, going back to worrying about water ingress, but also performance when we think about material for equatorial, where it's really highly humid region. But also we think about the reactivity. So we have those local feldspathic rocks that are being included. What is their reactivity? What is their fit? And what is their role in this case? So one thing that we observe is that we're going to have dissolution. So those inclusions that we're seeing here are going to react and they're going to be dissolved. So we can see that the raw material particle size is going to decrease because they dissolve to form the binder phase. But we still have some residual phase that come because it's only a partial dissolution. So we have both a filler effect, but we also have a catalysis effect. And when it dissolves and to form the binder, using machine learning method, we can actually look closely at that geopolymer gel. And what we've seen is that we have two forms of geopolymer gel created. We have one which is polysilicate, and then the other one is going to be sodium aluminosilicate hydrate gel. And those two different gel are going to have different morphology, but also different mechanical properties. So what we obtain from this collaboration is really a guide to be able to select appropriate raw material depending on the application. We can also provide quality control of the final products. And in general, we can then elucidate basic structure properties relationship in geopolymer composite. So in conclusion, we have a lot of grand societal challenges. I talked about, in this case, we had promote urban growth, promote sustainability, and also boost resiliences. And it's really important to be able to have collaboration between the US and the African continent. In terms of nanotechnology, I highlighted three different approaches, either using Portland cement with nanomaterial incorporated within it, or recycling concrete, or also just kind of getting over with cement and using, in this case, geopolymer, which is going to be a green alternative to cement. And another approach actually that is kind of leading us still building on geopolymer is to say, well, we can have geopolymer, but this time we're going to select our material locally because we want to be able to valorize local material and still have something that will have an equivalent performance. This in turn is going to lead to innovative materials design, and that will enable us to have solutions that are going to be fitted and suitable for the local context. So I want to thank again my students and also thank my sponsors for supporting our work. So thank you very much.